Welcome guys to a quick little video, and right now I am working on a simple PID control loop. And the setup is nothing much, but there you can see a small DC motor. It used to have a opto encoder disk and the dual opto encoding system like this has two slits inside, and from opto disk it counts the number of rotation as well as the direction, so precise uh, rotation can be followed. But in this setup I have approached a different encoding method. There you can see two Hall effect sensors that are mounted a certain distance apart across the shaft, that is uh, some magnet that you can see is glued to the shaft so that the Hall sensor can read the magnets. And this configuration is quadrature encoding, so the rising and falling edge is also being counted on this setup, and a crude rudimentary connection that you can see, small cable patch going into the microcontroller. I don't have any other fancy microcontroller, but I do have Arduino on hand, so I'm going to I'm currently playing with this. In the setup window we have a PID loop that is running on 1 kilohertz, and right now I was just messing around with different PID values. So my project idea is I am going to mount the motor as it is. I'm going to show you what this motor has been through, what is its actual work. So there you can see it was a part of a printer. I am going to use the printer scanner, the base of this printer scanner as a main axial platform. And the way that it works is, you can see small little grooves that are in indentation or teeth that are in the base actually. And this is a scanner part, and this has this goes over to this area, so the teeth align with this gear system, and the motor, the worm gear motor actually attaches to this one. This one goes to gear reduction to this, and this one drives through this rail. So we are going to write a PID loop for to control the motor, and essentially controlling this whole rail as a axis that I'm going to later put in use as a 3D printer, I think. So that is the main idea. I do have some other things in hand right now. I'm working. This is one of the belt drive section that I was repurposing for another access movement that you can see. It works, but the all these motors are DC motors, so I need some kind of encoding system in order to get any data of the position. I can buy a stepper motor and drive this, but who wants a stepper motor? Everybody is running around for the servo. So let's go over to the servo loop and let me show you how I tune my PID. So in this setup that you can see, the Hall sensor is actually connected in a rudimentary way. The two Hall outputs are being used as the input to two of the pins, analog pins, and two of the PWM output is going to the L298 edge bridge driver that is driving the motor directly through this ribbon cable, so that flexibility is our option. And the whole supply is running about 5.7 volt plus or minus, and we are right now calibrating the PID control. So let me show you how PID actually does things. I'm not going to go all over for the programming part, but it might vary for your motor, your perspective. But let me show you a cool thing that I have that you every PWM guy loves and sees. The PID guys know about this. So there you can see PID values start with small and slowly go bigger. So right now the KP factor is, I have set it around 5, and the integration factor is set at 2.22, and the derivation constant is 0.8 0.08, sorry. So in this setup, let's give it a position command and see what position can it do. So let's go over to the small step version. So let's see how the first let's see how proportional works. So the P factor actually represents that the how hard the system will work to get everything in proportion in the proportion factor. So let's give it a bit of big steps. So let's say P100, let's start with 100, and then we will slowly get much lower and much higher. So let's go over to the P100 and let's see what actually achieves by this motor. So I have entered hit, and there you can see the motor reached the value of 83 and slowly crawling. If I can show you the motor crawl, it is buzzing right now, and slowly the encoder disk you can see is actually rotating, and there you can see error value is slowly decreasing. So it is right now 7 and 6 and slowly getting 5, and it will crawl back to the desired position, and it will count over to the actual desired set point. So that is the one of the long loops. So let's try to use much more stronger force on the system. So let's give it a command of P, let's say 500. So it's quite long steps, so I don't have another hand, but if I can show you, so I have hit enter, and there you can see it is rotating quite fast actually, but it still comes down to the error factor of around 32, and I don't hear anything. Something has glitched or something like. So it is working, but slowly. There you can see slowly rotating and coming over to the 28, 27, 26. So I have to change the value. So let's so this is the typical problem of the integration constant. So ki constant is that you have to increase the value, because you can see this is not overshooting, this is lagging, and this is slowly crawling back to this its original, because it is counting the error and adding the error to compensate the differentiation, and then the value is such low that it does not have the driving force to go over to its desired set point. So that is why if you increase the I value, so it will crawl much more faster, so essentially mainly driving the motor. So let's increase the integration value, and let's see how the system actually response. So let's go over let's put 3 instead of 2. Let's see, slowly incrementing, because you don't want your system to be to get unstable. So let's try to upload this, and let's see how the system actually responds. So right now this is compiling, and I think we have some connection problems, so wait a minute. So the code is actually uploading. So this is the main challenge that you have to face in order to have a smooth drive of any kind of servo loop. So each servo drive you have to calibrate with your system, because the whole system is actually made up with kind of DIY fashion, so you have to do this. So our code is being uploaded, and let's give it a bit of command, and let's see how the system actually uh, responds. So let's give it a typical P100, and let's see how the system actually responds. There you can see it has reached kind of you can see much less error factor, because right now the error initially was 6 and then 5 and slowly crawling back and going around 2 and 1 it has reached. So the error actually it reaches much more faster actually. So let's put a more drastic value. Let's give it around 600. So let's start with 600. So that's actually rotating, you can see, but the error is right now is much more bigger, because more steps, more error, and it needs to integrate more in order to get more desired steps in order to drive the system. So you have to fine tune your own setup according to this value. So in our case we have to increase the differential value